I put my hand in a 200-degree oven. Actually, I'll put my whole head in there. I could hang out here all day. But if I put my hand in a 200-degree pot of water, same temperature, but oh! I'm not putting my head in there. The water feels way hotter at the same temperature, but is it hotter though? Now I'm cooking a chicken breast in the oven at 200 degrees and one in 200 degrees water. Same temperature, but the water chicken cooked in 30 minutes and the oven chicken took 2 hours. That's really weird. Maybe water is special though, so let's just use my oven. I'm cooking one chicken breast in the oven at 350 Fahrenheit and one in the air fryer at 350. Same temperature, but the air fryer chicken cooks faster. But maybe that's just because everyone's oven and air fryer is different, so let's try some stovetop cooking. I'm heating a thick cast iron pan and a smaller thin aluminum pan to 500 degrees. Now I'm cooking some Wagyu beef medallions on them. Wow, the cast iron pan cooked the beef way faster even though both pans were at the same temperature. Better sear on the cast iron too. Okay temperature, you've got some explaining to do. How did we get such radically different results at the same cooking temperature? Well, it's because heat is cooking your food, not temperature. Yes, they're different. When I bake a loaf of bread in my oven, I'm not moving temperature into it, I'm moving energy into it. That energy goes mainly into raising the temperature and evaporating water, and some of it goes into the various chemical reactions involved in cooking. For example, let's say I need to transfer roughly 500 kilojoules of energy into this bread to fully bake it. That transfer of energy from the hotter oven air to the colder dough is what we call heat. Hotter molecules in the oven air have more kinetic energy. That means they move faster, they vibrate more, and they constantly collide with slower molecules, spreading that energy out until it reaches equilibrium. And this used to confuse me because I always wondered, how does heat speed up molecules? Heat is like touching a hot stove and speed is like driving my car on the highway. Those are completely different things, right? Yes, in our everyday experience, they seem different, but at the atomic level, they are fundamentally related. Let's go back to my sourdough. When I say I'm heating this dough by 500 kilojoules, what that really means is I'm increasing the bread's internal energy by 500 kilojoules. Think of internal energy as the sum of all energy contained within the bread. That means the kinetic energy of the vibrating molecules and the chemical potential energy stored within the bonds that hold molecules together and hold molecules to each other. So we need 500 kilojoules to cook this bread. Kilo means 1,000, so 500 times 1,000 is 500,000 joules. A joule is a unit of energy, and when you break it down into its base units, it works out to 1 kilogram meter squared per second squared. That looks kind of familiar. We have meters per second in there, which is a measure of speed, just like miles per hour, and that means energy in the form of heat is fundamentally related to speed. So when I heat my bread to 500 kilojoules, I'm actually bombarding that bread with trillions of little molecules going faster than the molecules in the bread. Now, technically, I should be saying more kinetic energy because kinetic energy includes mass as well as speed, but it's easier just to think of it as faster molecules in this example. So when those faster molecules of air hit the bread molecules, they're transferring that speed to them, just like this ball hits the other ball and transfers motion to it. Some of the energy from those molecular collisions increases the average speed of the molecules in the bread. Some of it is used to break and reform molecular bonds, some of it turns liquid water into steam, some of it speeds up the rate at which yeast eats the sugars in the bread and produces CO2 gas, responsible for those little air pockets in the bread, and that's how we end up with a fully cooked loaf of bread. But where does temperature fit into this? We know that we need 500 kilojoules of energy to cook this bread, but we can't just set our oven to 500 kilojoules. This isn't Star Trek. Luckily, some smart people a long time ago figured out that the level of liquid mercury in a sealed tube is related to how hot or cold it is outside. They put some marks on the tube and called that temperature, measured in degrees Fahrenheit. 32 degrees is when water freezes, 212 degrees at sea level is when water boils. Those numbers divide easily into fractions, and we didn't have calculators at the time, so we rolled with it. Celsius came a bit later based on a freezing point of 0 degrees and a boiling point of 100 degrees when the metric system came into vogue. We later realized that bimetal coils spring to the same position at the same temperature, so we got analog thermometers. And we learned that changes in voltage and electrical resistance are related to temperature as well, so we got thermocouples and thermistors. And in the future, maybe thermoses. Then some math wizards figured out that temperature is actually related to molecular motion, and molecular motion kind of stops at negative 273.15 degrees Celsius. They said, that's kind of weird. Let's make a new temperature scale and call it Kelvin, which starts at 0 when there's no molecular motion, mostly, and goes up from there as molecular motion increases. Luckily, they made each increment of Kelvin the same magnitude as a degree Celsius, so we can still use degrees Celsius in a lot of math equations where we're only dealing with the difference in temperature or the delta in temperature, like this specific heat formula, for example. But we need to use Kelvin where the equation pegs temperature in reference to absolute zero, like the most OG of all science equations, the ideal gas law. PV equals nRT. Now at this point you're probably thinking, wow Steve, I just wanted a brief overview, I didn't want an entire lecture. Well, in order to understand this stuff, you gotta go deep, and we're gonna go deep. Okay, now that we had a temperature scale that measures actual molecular motion, also known as kinetic energy, we could say every increase in a unit of Kelvin represents a fixed and known increase in average kinetic energy per molecule. And this is really, really important to understand. Temperature is based on the average kinetic energy per molecule in the system. Or said another way, hotter temperature means faster molecules. So your oven thermometer is not telling you the amount of energy being transferred to your bread in the form of heat, aka the thing that's actually cooking it. No, it's telling you the average speed of a molecule in your oven without telling you how many molecules there are, how fast it's transferring heat in your oven, or any of the other stuff you really need to know to figure out how fast your food is gonna cook. So temperature is kind of like a speedometer. It measures how fast you're going, which is kind of useful so we don't get a speeding ticket, but it doesn't measure how far you have to go or when you're going to get there, which is the information we actually want when we drive our car to go somewhere. And that's why in scientific lingo, temperature is called an intensive property. That means it doesn't depend on the amount of it that you have, it only gives you a rate, something divided by something. Now, heat, on the other hand, is what we call an extensive property. It depends on the amount of energy you transferred. It's just one number, kilojoules. Kind of like saying I have to travel 500 miles to get somewhere, or it's going to take me 2 hours to get somewhere, as opposed to temperature, which is I'm traveling 50 miles per hour. Now, it's this extensive property of heat that is one of the reasons why I can easily stick my hand in a 200-degree oven. Air is not very dense. It has relatively few molecules, which are the things that carry energy. That means even though the air molecules are at 200 degrees, there's not a lot of them. So when a few of them hit my hand, they might be going pretty fast, but there's not a lot of them, so they're not transferring a lot of energy. But when I put my hand into 200 degrees water, same temperature, but it burns me immediately. And that's because water is much denser than air. It has more molecules packed in per unit of volume, all at 200 degrees. So when I dip my finger in it, there's more molecules bombarding my finger and transferring energy to it, which cooks my finger much faster. Now there's another reason why water feels much hotter than air at the same temperature, but we'll get to that later. So why do we use temperature in cooking when it only tells us how hot molecules are on average? It doesn't tell us how much actual heat energy is being transferred to our food over what period of time, which is what we actually want to know. Well, the answer is pretty simple. It's because we can easily measure temperature with a thermometer. We can't easily measure the transfer of heat energy in our oven. Not only that, when you pair temperature with time in a recipe, it gives us a rough language to communicate how to cook something and get similar results. For example, a standard bread recipe might say cook bread in oven at 375 degrees Fahrenheit for 30 minutes. That's going to work pretty well in most cases because most ovens are a similar size, they transfer heat in a similar way, they're all using air as the medium to transfer energy. But we've all had this happen before. If you and me follow the same recipe and both cook bread in our oven at 375 for 30 minutes, mine might turn out perfect in 30 minutes, but yours might take an hour. And the crust is thicker, it's drier, it's harder, and it's burnt on the bottom. And the reason for that is because we're just cooking with temperature and time. So even though both our loaves of bread need the same amount of energy to fully bake, let's call it 500 kilojoules, your oven might transfer that energy to the bread much slower than mine for several reasons. Maybe the oven is on convection mode rather than regular bake mode. Maybe you're using a loaf pan that's made of a thicker or different material than mine. Aluminum, steel, cast iron. Maybe you shaped your loaf of bread a different shape than mine. Maybe you let it rise longer. These are the next level considerations that allow us to still use time and temperature in a recipe, but also think about the factors that influence how heat is being transferred to the food over time, because that's what's ultimately cooking our food. So those next level considerations are what I'm going to talk about next. There are 3 ways that heat moves: conduction, convection, and radiation. Conduction is heat transfer through direct contact. Molecules bump into other molecules and spread out their kinetic energy, like in our ball hitting the other ball example. This is primarily how food gets cooked. The hot air around the food or the hot pan on the stove is much hotter than the food, so it creates a difference in temperature. Heat always flows from hotter temperature areas to lower temperature areas, so all of those super energetic molecules in the hot area blast and bump their way into the exterior molecules of the colder food. The exterior surface of the food then heats up and rises in temperature slowly, and those energetic molecules near the surface start bumping into the next band of interior molecules, transferring a little bit of energy to them. Then that band of molecules heats up the next one, and so on into the interior of the food. Now, the hotter the heat source outside of the food and the colder the food, the faster the heat is going to migrate to the center because there's a greater temperature difference between the outside and the inside. In scientific lingo, this is called diffusion, and it's really important to understand. Let's take this steak as an example. If we cook it on a screaming hot grill, the heat is going to diffuse into the meat really quickly and unevenly. It's going to overcook the exterior, and by the time the center gets to our target temperature of, let's say, 135 degrees Fahrenheit for medium rare, the exterior is already overcooked. Let's say it's over 165 degrees Fahrenheit, and we just get this little bullseye of medium rare in the center, which is not what we want. We want rosy pink medium rare all the way through. Well, at least I do. Maybe you like well done steak. You do you. To make matters worse, we might temp the center of the steak and it says 135, but if we leave it sitting there for 10 minutes, there's so much energy left over in those exterior bands that it's going to keep cooking the interior bands well above 135. That's called carryover cooking. So if we want that same medium rare temperature throughout, there's two things we can do. First, we can cook it at a high temperature until the center gets to a certain temperature, let's say 120, well below our target of 135, and then we pull it off the heat source and let carryover cooking take it up to 135. So we're using the reservoir of energy in those exterior bands of the steak to slowly cook the center up to 135 after we remove it from the heat source. This is really hard to do though, and it takes a lot of experience, but there's a much easier method. An easier way is to cook the steak longer at a lower temperature so the heat slowly diffuses into the meat over time and comes up to an equilibrium temperature of 135. How do you do that? Well, you could use a sous vide machine or your oven set very low to cook the steak up to 135 to lock in that temperature, then rest it down on the counter. There's not going to be any carryover cooking because we cooked it at such a low temperature that those exterior gradient bands of the steak aren't holding enough energy to continue to cook the interior. Then after it's rested down to, let's say, 110 or 120 degrees Fahrenheit, we give it a quick sear and we slice into it. This method is called the reverse sear. So that is conduction, molecules bumping into the next closest molecule to transfer energy. Now let's talk about convection. Convection is heat transfer by a moving fluid, which includes air, water, steam, or oil. Unlike conduction, which is all about molecules really close to each other, bumping into each other and transferring heat energy, convection involves big currents of liquid or air moving around and taking those energetic molecules to the surface of your food, where they then start bumping into each other and transferring energy via conduction. Let's say I'm cooking a brisket in my smoker. We have big convective air currents carrying hot, energetic molecules to the surface of the brisket, transferring that energy to the surface and losing some of their own energy, but then boom, 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 another fresh batch of hot, energetic molecules is getting moved in right behind them via convection, and so on. So convection transfers heat really effectively because those big convective currents are constantly moving hot molecules to the surface. Now, remember when we talked about how water cooks food faster? That's because water is much denser than air, so it has more molecules getting swept to the surface of the food via convection and then transferring their kinetic energy to the food via conduction. If my hands are like 2 molecules of air in my oven slowly slapping the meat every second with my pathetic soy boy slaps, then boiling this brisket in water would be like 200 Bruce Lee fists hitting it every second. Now, what about our example at the start of this video where we talked about cooking chicken in an oven versus an air fryer? Why does the air fryer cook our chicken faster? Well, air is not very dense. It doesn't carry a lot of energy, but if we speed it up, it increases its flow rate. Then it transfers energy much more quickly. There's a few reasons for that. For one, fast-moving air blows away the colder boundary layer around your food, so the surface heats up faster. But the main reason is simply that by speeding up the airflow, we're increasing the amount of molecules hitting that meat per second. So even if our oven and the air fryer are both set to 350 degrees Fahrenheit, the air fryer is peppering and bombarding that chicken with way way more 350-degree molecules of air per second, so it heats up faster. This is the same reason your oven cooks faster on convection mode, which just means a fan is turned on that moves air around the oven. An air fryer is like convection mode in your oven taken to the extreme. So if you want a quick way to remember it, convection is what brings heat to the surface of your food, and conduction is what transfers it to the interior. Finally, let's talk about heat transfer via radiation. I know it sounds scary, but in science terms, radiation is really around us everywhere, and for the most part, it's pretty harmless. In fact, visible light is radiation, and so is infrared radiation, which is what we're mainly concerned with in cooking. These are all forms of electromagnetic radiation, and it's spread out on a spectrum of super highly energetic melts your brain, all the way to harmless radio waves that deliver soothing tunes to your car radio. With cooking, we're concerned with infrared radiation, which falls somewhere between those two extremes. Radiation cooks food by bombarding the molecules of the food with electromagnetic waves. Those waves hit the molecules of food and transfer some of their energy to them. This increases their kinetic energy, aka it heats them up and makes them go faster, and this transfer of heat happens without heating up anything between the heat source and the food. It's mostly just a transfer of energy from object to object. Everything emits infrared radiation. Yes, you are emitting infrared radiation right now. But when something gets really hot, it emits exponentially more radiation. A cold pizza stone in your oven at 20 degrees Celsius might only emit around 25 kilojoules of energy per minute, but at 400 degrees Celsius, it might emit upwards of 700 kilojoules of radiant heat energy per minute. That's 20 times higher temperature, but it's transferring almost 30 times more energy. So radiant heat transfer increases a lot more than you'd expect as you go up in temperature. But it also exponentially decreases as you increase the distance from the heat source. Every time you double the distance of your food from a point source of radiation, which isn't exactly realistic because a lot of sources of radiation are not point sources, this is just for illustrative purposes, it drops the intensity of the radiation by 4 times. So if I'm cooking a steak on the grill 1 inch from the coals and I say to myself, I want to decrease the intensity of the heat by half, so I'll double the distance from the coals. Nope, you're actually decreasing the intensity of the heat by a lot more than that. And vice versa, if you want to increase the intensity of your heat by dropping that steak closer to the coals, you have to be really careful because the closer you get, that radiant heat exponentially increases in temperature. Okay, how do these 3 modes of heat transfer, conduction, convection, and radiation, all fit together into a mental model? Well, let's take cooking chicken in the oven as an example. Let's say I preheat my oven to 400 degrees Fahrenheit and then place a chicken breast in the middle of the oven. And I put another piece of chicken right next to the oven wall. Which one is going to cook faster? Well, we've got convective heat going equally around each chicken breast at the same temperature of 400 degrees in the oven. That hot convective air is transferring energy to the surface of the chicken, and then conduction is taking over and cooking the inside. But the one close to the wall on the right is also receiving a big dose of radiant energy from the wall of the oven. So both pieces of chicken are cooking at the same air temperature, but the one closest to the wall is cooking faster because it receives more heat. Now, you would have no idea if you were just following a recipe that says 400 degrees for 30 minutes and your chicken is done. Well, it's gonna cook a lot faster if it's close to the oven wall and you've been preheating the oven for an hour before you put the chicken in, which means that the wall of the oven is fully heat soaked and emitting a lot of radiation. But what if I put those chicken breasts on a thick cast iron pan or aluminum tray rather than a sheet of aluminum foil? Would that make a difference? Oh, you better believe it. And the reason for that is specific heat capacity. What is specific heat capacity and why does it matter in cooking? Specific heat capacity is defined as how much energy it takes to raise the temperature of 1 kilogram of material by 1 degrees Celsius or Kelvin. Here's the equation for specific heat capacity. It says that Q, which is the change in heat energy, equals mass times specific heat capacity times the change in temperature of the material. So, for example, aluminum has a specific heat capacity of 0.90 kilojoules per kilogram Celsius degree. 2 objects made of the same material but with different masses will hold on to different amounts of energy according to this equation. For example, let's assume we heat both the pan and the foil up by exactly 150 Celsius degrees. degrees. Run the math, and the pan gains 135 kilojoules of energy, but the foil only gains 0.675 kilojoules because its mass is so much smaller. Same material, but the pan has more of it. That means it has more aluminum atoms all buzzing and shaking in their solid metallic lattice structure, so there's more kinetic energy overall in the pan than there is in the thin piece of foil, even though on average all of the atoms are moving at the same speed, i.e. the same temperature. Pretty intuitive to understand. More mass equals more energy at the same temperature and the same material. But here's where it gets interesting. Different materials hold different amounts of energy at the same temperature, even if they have the same mass. For example, this 1 kilogram aluminum pan can hold on to more energy than this 1 kilogram cast iron pan at the same temperature because it has a higher specific heat capacity. Why does aluminum have a higher specific heat capacity? Aluminum has a lower molar mass than iron. That means an atom of aluminum weighs less than an atom of iron. So a kilogram of aluminum has more atoms than a kilogram of iron. Just like a kilogram of feathers has way more feathers than a kilogram of bricks. Now, because there's way more aluminum atoms all moving and shaking in our kilogram of aluminum, it has more energy overall than the kilogram of iron, even though all the atoms in both materials are moving at the same average speed, i.e. they are at the same temperature. So because our 1 kilogram aluminum pan has a higher specific heat capacity and can hold on to more energy at the same temperature, it's going to transfer heat faster than our kilogram iron pan. And when a cold piece of chicken hits the aluminum pan, it's going to drop the temperature of the pan by less because it has more energy available to absorb that initial cold shock. Therefore, our food will cook faster. Let's look at our equation again. We're going to keep our aluminum pan, but we're going to add the 1 kilogram iron pan now. The kilogram iron pan is the same weight and it's going up by the same temperature as the aluminum pan. The only difference is its specific heat capacity is lower. Run the math and we get 135 kilojoules for the aluminum pan and just 67.5 kilojoules for the iron pan. So the aluminum pan gained more energy and therefore it's going to have more energy to transfer to our food in the form of heat. But if this is the case, then why in reality do cast iron pans hold on to more energy and give our food a better sear? Well, it's because of density. Iron atoms are much heavier than aluminum atoms. Therefore, cast iron pans are way heavier than aluminum pans of the same size, at least double the weight. And remember, in our specific heat equation, mass has a big impact on how much energy the material can hold. So let's get rid of this tiny 1 kilogram cast iron pan. It's a little bit unrealistic, and we'll use this 10-inch cast iron pan instead. Same size and volume as the 1 kilogram aluminum pan, but the cast iron pan weighs 3 kilograms. So when we run the math, the heavier iron pan gains 202.5 kilojoules, but the aluminum pan only gains 135 kilojoules. So the aluminum has a higher specific heat capacity, but the cast iron pan is able to absorb more energy at the same temperature because it weighs a lot more for the same amount of volume. This is why cast iron is prized for its ability to retain heat and sear meat so effectively. It's because even though aluminum stores more heat per kilogram, cast iron is much more dense and heavy for the same size of pan, so it stores more heat. Because it stores more heat, when a cold piece of chicken hits the cast iron pan, the pan barely drops in temperature, so it gives a better sear. Okay, I'm sold. Let's throw out all our other pans and just replace them with cast iron, right? Well, not exactly. There's another property of pans we need to think about before we crown cast iron as the king of the kitchen, and that is thermal conductivity. Conductivity is a measure of how easily heat moves through a material. Aluminum has a much higher thermal conductivity than cast iron. So if I heat one part of an aluminum pan, that heat spreads through the pan much more quickly. So now we've got two different ideas. One is specific heat capacity. That's how much energy the pan can hold per unit of mass. The other is conductivity, how fast the energy moves through the pan. And when we combine those two ideas together, we get thermal diffusivity, which is a measure of how fast heat moves through a material after accounting for both specific heat capacity and conductivity. Aluminum has cast iron beat in this regard because it has both a higher specific heat capacity and a higher conductivity. So the temperature of an aluminum pan changes much more quickly when you adjust the burner. This means with aluminum pans, heat is going to get transferred to the food much more quickly when we go from a cold pan. To demonstrate this, I poured some egg whites in a cast iron pan and set it over a small burner on low heat. You can see how the egg whites cook only where the burner flame is hitting the bottom of the pan, very uneven. But when I do the same thing with the aluminum pan, we get a solid white circle of cooking and much more even heating. Then I used my IR camera to look at how the pan's heated. Again, you can see the cast iron pan heats up very slowly and unevenly, and the aluminum pan heats up much more quickly and evenly. That's simply because aluminum is more conductive. So because aluminum responds much more quickly to temperature changes and heats up more evenly, it's good for cooking delicate foods like hollandaise sauce or buffalo sauce with hot sauce and butter. In either case, if you go over 150 degrees Fahrenheit with either of these sauces, the emulsion will break and you'll need to start again, which is not a good thing. So having a pan that responds quickly to temperature adjustments is a huge advantage. You wouldn't want to use a cast iron pan that doesn't respond when you turn the heat down. It would just continue to cook the sauce until the emulsion breaks. On the other hand, you need to be really careful with aluminum pans because they can transfer the heat from the burner to the food so quickly that you can scorch it. So precise temperature control is much more important with aluminum pans. On the other hand, if I'm searing meat, I will always reach for my cast iron because once you preheat it, it holds onto a ton of energy and it barely blinks an eye when you put a cold piece of meat into the pan. So it's going to transfer heat really quickly. It won't drop in temperature that much, and that will result in a better sear. Now, obviously, your choice of pans is not just limited to aluminum versus cast iron. I just used those two examples because they're on opposite sides of two extremes. On one side, we have cast iron and carbon steel. These are on the low specific heat capacity, high density, low conductivity side of the spectrum. So they're good at holding onto heat and searing because of their high density. And on the other side of the spectrum, we have aluminum and copper pans, which are highly conductive and have a higher specific heat capacity. These are better for precision temperature control and even heating. Then in the middle, we have hybrid pans, which most of us have in our kitchens. They're alternating layers of materials such as the popular tri-ply pan, which is a layer of steel, then a layer of aluminum, and then another layer of steel. They strike a balance between conductivity and heat retention, but they're not as good at searing as cast iron, and they're not as conductive and responsive to temperature changes as pure aluminum or pure copper. Okay, now let's talk about water because it's really special. Water is the GOAT of specific heat capacity. It takes 4.18 kilojoules to raise a kilogram of water by 1 Celsius degree. In comparison, air is 1.0, aluminum is 0.9, cast iron is around 0.5. If we think of specific heat capacity as a material's ability to hold on to energy, then water beats out every other material even when it's at the same temperature. Not only is water more dense than air, which means more moving molecules and therefore more energy transfer, it also holds on to more energy per molecule. So we talked about an air fryer doing 100 Bruce Lee punches per second on your food. Water at the same temperature as your air fryer is like 500 Bruce Lee punches per second. And that's why boiling food at just 212 degrees Fahrenheit cooks the food way faster than in an oven at 212 degrees Fahrenheit. The increased density and higher specific heat capacity of the water greatly influences the heat transfer coefficient, or how fast a fluid medium transfers heat. The heat transfer coefficient also depends on fluid velocity, conductivity, and other factors, but this is the main reason water feels way hotter than air at the same temperature. There's simply more molecules in the water per unit of volume, and they hold on to more energy. But why does water have a higher specific heat capacity than all of these other materials? What makes it so special? It's because of hydrogen bonds. Hydrogen bonds are intermolecular bonds between different molecules of water, not the intramolecular covalent bonds holding the H's and the O's within each molecule of water. We're talking about the forces attracting water molecules to each other. Each water molecule is polar. That means it has a more negative end and a more positive end, kind of like a magnet. The negative end with the oxygen atom is attracted to the positive end of the hydrogen atom of the neighboring water molecules. So each water molecule is attracted to 4 neighboring water molecules like a bunch of weirdly shaped magnets. In other fluids like air or oil, the molecules are only attracted to maybe 1, 2, or 3 max other molecules at any given time, not 4 like with water. So it's this ability to be simultaneously attracted to 4 other water molecules at any given time that we call a hydrogen bond. And it's what makes water behave in really special ways. When you add heat energy to water, the energy has 2 main places to go. First, it can increase molecular motion, so increasing the speed of molecules like we talked about before. This raises the temperature. Or second, it can go into disrupting and rearranging those hydrogen bonds between water molecules, which does not raise the temperature of the water. In water, a significant portion of the energy we put into it is going into just trying to overcome those hydrogen bonds between water molecules because it needs to weaken those bonds before the energy can actually go into speeding up those molecules and increasing increasing the temperature. Now, because a lot of energy is constantly being taken up in disrupting those hydrogen bonds, it takes a lot more energy to increase the temperature of 1 kilogram of water by 1 Celsius degree. That's why water's specific heat capacity is so much higher, and that's why it can hold on to and therefore transfer so much more energy than other mediums. For example, you're going to dinner at your brother-in-law's house and you're bringing, let's call it chicken thighs. It's a 30-minute drive to get to your brother-in-law's house. So are you going to cook the thighs in the oven, transfer them to a thin aluminum pan, and then put them in your car? No, because they're going to be cold by the time you get there 30 minutes later. What you're going to do is sear them, then put them in a cast iron pot in the oven, braise them in some sort of liquid until they're done, and then take the whole pot, including the braising liquid, with you in the car. The energy stored in all of that water in the braising liquid is going to keep those suckers screaming hot until dinner time because water holds on to so much heat. So TLDR, water holds on to way more heat than other stuff, but it also has another superpower, a kind of built-in temperature safety limit that makes it really useful for cooking. Let me explain. To raise the temperature of liquid water by 1 Celsius degree, you need 4.18 kilojoules of energy. That's its specific heat capacity. Now, we can see and feel that temperature of the water is going up as we put this energy into the water, and that's why we call it sensible heat. But once you hit the boiling point, let's call it 100 degrees Celsius or 212 degrees Fahrenheit at sea level, you all of a sudden need 2,257 kilojoules per kilogram to convert that water into steam. That's what we call the latent heat of vaporization. All the heat going into the water once it hits its boiling point is now going into turning that liquid water into steam, and it's not going into raising the temperature of the water. We know there's energy going into the water, but we can't feel or see the rise in temperature, so we call it latent heat, which means it's hidden to us. We can't sense it. Then after the water turns into steam, any additional energy we add to the steam will go into raising the steam's temperature. So where's all that heat going once the water starts to boil? Again, it's going into breaking the hydrogen bonds between the H2O molecules. It takes a lot of energy to rip those water molecules apart so they can escape in the form of steam. It's kind of like these two fridge magnets that I stuck together. I can easily move them around. That's like increasing the temperature, but when I try to force them apart, that takes a lot more energy. That is like converting liquid water into steam, the latent heat of vaporization. And now, once it's in steam form, they're again a lot easier to move around and increase in temperature. Now, why is all of this important? Well, here's a couple reasons. One, if your food has a lot of water in it, like a big hunk of roast beef, it's going to take a lot longer to cook because you need to put enough energy into the meat to heat up the water in it, which takes a lot of energy because of the extremely high specific heat capacity of water. That water then needs to migrate to the surface so it can either drip out or evaporate into water vapor, which, because of the very high latent heat of vaporization, again takes a ton of energy. And if you're boiling a big pot of water on the stove, that's one of the most energy intensive things you can do. So give yourself a head start by starting with hot water from the sink and cover the pot. I like to use these ThermoWorks high temp silicone pot lids to do that. This traps the hot steam in and your water will boil much faster. Also, if you're boiling things like pasta or potatoes, only use enough water to cover the food. Excess water is just going to take a lot more energy and time to heat up, and it's not doing anything. Second, the boiling point of water is 212 degrees Fahrenheit or lower depending on your elevation. It will be lower if you live at a higher elevation. This can be used as a kind of guaranteed temperature limit so you don't overcook or burn certain foods. You don't have this temperature safety limit when you're cooking with things like oil, which can get up to 400 degrees, or a hot pan, which can get up to 600 degrees plus. But with water, we're guaranteed to not go above the boiling point of water, which is 212 degrees Fahrenheit, unless we use a pressure cooker. So we can braise meat with liquid in the pot so it cooks low and slow and gently renders the collagen over time. We could put a bit of water in the pan with our pot stickers to slowly bring them up in temperature. Then all the water boils off and the temperature starts to rise and fries them for that final crispy sear. We can add a bit of water to the pan when we fry bacon, so the bacon cooks no higher than 212 degrees Fahrenheit. It renders the collagen, relaxes the muscle fibers. Then when the water boils off and the temperature goes way up to crisp the bacon, the strips are lying more flat and they don't bunch up and cook unevenly. When I make Greek potatoes, I add water and lemon juice as well as oil, so during the first part of the cook, we're guaranteed to be below 212 degrees Fahrenheit and the potatoes are gently parboiling. Then the water evaporates and the oil starts taking over and rising in temperature and fries them for that crispy finish. Oh, and here's a pro science tip. If you're planning on braising something in the oven, don't just put it in the oven cold. It's going to take forever to heat up that water. Instead, boil it on the stovetop first, then transfer it to the oven, and that's going to greatly decrease your cooking time. And why is that? Because the air in in the oven is much less effective at transferring heat than your stove is. And finally, 3, we can use water's ability to hold on to heat to cook food faster or more evenly, or keep it warm for longer, or even defrost food faster. For example, I just got home from work and I need to cook this frozen block of ground beef in 5 minutes before the kids have a meltdown. Am I gonna put it in the microwave to defrost for 20 minutes? No, I'm gonna chuck it in a pan with hot water, boil it and flip it and scrape it until it's all defrosted. I could strain it right now and serve it, or if I have a little bit more time, I could let the water boil off and sizzle it up in its own fat. Boom, taco night's back on. Instead of giving up like most people would, I cooked a solid block of ground beef in 5 minutes. Another example, I'm going to Uncle Jim's tonight and bringing dinner. Guess what? I'm using the crock pot because it's gonna stay warm for a lot longer in the car ride over there. Gotta cook a turkey today, but it's frozen solid. Hot water for an hour, then spatchcock it, then cook it. Boom, turkey's cooked from frozen in under 3 hours. Well, Jim next door started defrosting his in the fridge 9 days ago, and his turkey is still cooking after 6 hours. Now you know the difference between temperature and heat, and I hope it makes you a better cook. Until next time, keep experimenting and keep improving.